We want to spend just a moment at this point talking about sex determination and sex linkage. You realize that the genes that we've talked about so far have all been located on these chromosomes we refer to as autosomal chromosomes, chromosomes that have nothing to do with sex determination. So in humans we have 46 chromosomes total, 44 of which are autosomal chromosomes. The last pair of chromosomes are referred to as the sex chromosomes, and they determine whether an individual is a male or a female. This is true in humans and many other animals, but not all animals. Alligators, for instance, do not have chromosomal sex determination. The sex in alligators determines on the temperature at which eggs are incubated. So we also want to talk about sex linkage in this particular part of our chapter. And so interestingly, the X and the Y chromosome are not the same. The X chromosome is a very large chromosome that contains many genes that have nothing to do with sex determination. The Y chromosome is very small and only has genes that pertain to sex determination. So in humans, if you have two X's, then you are a female, two X chromosomes that is. If you have an X chromosome and a Y chromosome, then you are a male. And so it's easy to see then that when a female produces eggs, all her eggs will have an X chromosome, and when a male produces sperm, his sperm will either contain a X chromosome or a Y chromosome in a 50-50 ratio. And so interestingly, in agriculture today, you can order sexed sperm when you are producing animals for your operation. And so if you're artificially inseminating cattle, then you can order X sperm if you want to produce all females, or Y sperm if you want to produce all bulls, for instance. Therefore, the fathers and not the mothers determine the sex of the offspring. We now want to spend just a little bit of time talking about X linkage or X-linked genes. These are genes that occur on that very large X chromosome that contains many genes that have nothing to do with sex determination. So interestingly, X-linked genes were discovered by a Lexington native. Thomas Hunt Morgan was a Lexington native who attended the University of Kentucky, got a degree in biology, and eventually he received a Nobel Prize for the discovery of X-linked genes. He became a very famous scientist. He was not at the University of Kentucky as a famous scientist. In fact, he rarely apparently came back and visited Lexington. But we were excited about that. We've only had 3 people from Kentucky ever to win a Nobel Prize, and only 2 of those went to the University of Kentucky. And so Thomas Hunt Morgan was one of these, and as a result of the fact that his field was biology, the biology building at the University of Kentucky is named after Thomas Hunt Morgan. He used fruit flies as a model organism, and as you can see on the screen, these are fruit flies. And interestingly, the X-linked trait that he discovered was white eyes. Next time you see fruit flies buzzing around in your kitchen, take a look at those fruit flies. They'll most likely have red eyes, like this fruit fly here. However, if you look closely and long enough, you might find a fruit fly that has white eyes. And white eyes in fruit flies is an X-linked trait, an X-linked mutation, interestingly. We want to spend just a moment talking about some X-linked mutations that are found in humans. One of the very well-known ones, is hemophilia. And so hemophilia is a disease that's caused by, or a disorder we might say, caused by a mutation in genes that code for clotting factors in the blood. If the mutation is present, then blood doesn't clot, and the people that have this mutation bleed and bleed and bleed, and oftentimes die as a result of blood loss because their blood cannot clot. And so, if we look at the inheritance of hemophilia, this is what we see. So, the little h here represents the mutated gene for blood clotting. And so, in other words, this is the gene for hemophilia. The absence of any notation on this X chromosome, what I'm pointing to on the screen here to the left, means that this X chromosome has a clotting gene that's completely normal. And so don't be confused by the fact that there is no H on that X chromosome. That simply means that the clotting factor gene is completely normal in that X chromosome. And so this female, interestingly, would be a carrier for hemophilia. This means that she has the gene, but she does not express the trait. And so this X-linked mutation, like others, all the others that we'll talk about, we're only going to talk about one other one, which is color blindness, is an example of complete dominance. As long as you have one normal gene found in this X chromosome, it completely covers up this recessive gene that is the mutation found on the other X chromosome. Now here we have a male. The males are more likely than females to express an X-linked trait because, as you can see, they have one chance to get a normal copy of the X chromosome. The key to understanding this is to realize that the Y chromosome is different, as I previously stated. It's very small, and it doesn't have the same genes. So males they are completely normal for hemophilia if they have a normal gene on this one X. But they've only got one chance to get a normal gene. This male didn't get it, so he does have hemophilia. So when these two individuals reproduce, you can see that this female will produce eggs that will have this 50% of the eggs will be normal, 50% of the eggs will have the gene for hemophilia. All of the male's X sperm will have the gene for hemophilia, and the male's Y sperm, of course, don't have that gene, so that doesn't play into this story at all. And so this means that half the females, these are females of course, and half the females are carriers, and then the other half have hemophilia. Of the males, half the males are normal, and the other half of the males have hemophilia. So interestingly, this is how X-linked genes are passed on. And so another very common X-linked mutation is color blindness. And you can easily do a little family tree and calculate whether or not you are colorblind based on whether your parents and grandparents are colorblind. In my case, my father is colorblind, but my mother and both of her parents are not colorblind. So she doesn't have any mutation for colorblindness on her X chromosomes, but my father does. Now I, as you would guess, as you no doubt have figured out here, am normal because my X chromosome came from my mother, my Y chromosome came from my father, and so her X chromosomes are normal, and therefore I am normal. My sisters are carriers, right? Because they got an X chromosome from my father, who is colorblind, and an X chromosome from my mother, who is normal. And then I have nieces and nephews, and so you can see that those nieces and nephews, the nieces, assuming that my brother-in-laws, and I'm not certain about this, but assuming that they are they're not colorblind, and so actually I am certain about this. My brother-in-laws are not colorblind, so that means that there's a 50% chance that my nieces will be carriers of color blindness, and then my nephew, there's a 50% chance that he will actually be colorblind. And it appears that he is colorblind, unfortunately. When he's looking at little stickers and things, he's only 2 years old. My nieces are easily able to pick out what's red and blue and purple and so forth, but he seems baffled by the colors there, likely because he is colorblind. And there'd be a 50% chance he's colorblind, since my sister is a carrier for that colorblind gene. So X linkage is a pretty basic form of inheritance. It's very interesting. It's quite different than genes found in autosomal chromosomes, but with just a little bit of knowledge, you can calculate whether those genes will show up, say, in your family if you have an ancestor that is colorblind.